Imagine stepping into like a super busy commercial kitchen.
Yeah.
Pots clanging, people yelling, and someone turns their back for just a minute, and a massive vat of cooking oil is suddenly burning at 600 degrees.
Oh, yeah. That is a terrifying situation.
Right. The heat is just blistering, and your immediate human instinct is to grab the nearest fire extinguisher off the wall, rush up to the fryer, and just blast that high-pressure stream directly down into the center of the flames.
Which is exactly what you should not do.
Exactly, because if you actually do that, you won't put out the fire. You will create like a localized bomb of boiling, burning napalm that just explodes across the entire room. So welcome to the deep dive.
It really is a worst-case scenario, and it happens because most of us operate on this very dangerous assumption. We think that all fires are exactly the same, and any extinguisher will just put them out.
Which brings us to today's source material. We are diving into a really comprehensive and honestly surprisingly intense training document. It's titled Extinguisher Performance Objectives and Details, .pdf.
It's a great source, super detailed.
Yeah, and our mission for this deep dive is to fundamentally transform how you view that, that red cylinder hanging in your office hallway or your apartment stairwell. We want to take it from a dusty metal tube that just kind of fades into the wallpaper to a highly precise instrument of chemical warfare.
I love that framing.
Yeah.
Because that shift in perspective is so crucial. We tend to view fire as just, a thing that happens, like a random event.
Right, like bad weather.
Exactly. But from a firefighting perspective, a fire is a living, breathing chemical equation. And to stop it, you don't just throw water at it and hope for the best. You have to break the math.
Break the math. I really love that concept.
Yeah.
But before we can look at the chemical weapons used to break that math, we have to classify the enemy.
We do.
Because flames actually have these almost biological-like vulnerabilities, and it depends entirely on what they are consuming. I know the training document meticulously breaks the enemy down into 5 distinct classes, but I want to understand how they actually behave differently in the real world. So let's start with Class A.
Sure. So Class A is your ordinary combustibles. Think wood, paper, cloth, rubber, your standard trap.
Basic stuff.
Right. These are solid materials that leave behind an ash. And the key thing here is they tend to burn deep and smolder. The heat literally burrows into the core of the material. So stopping a Class A fire requires soaking it all the way down to its bones.
Okay. But then we shift from solid fuels to liquid fuels, which brings us to Class B.
And this changes the battlefield completely. Class B involves flammable and combustible liquids and gases. We are talking oil, grease, paint, gasoline, solvents, alcohol.
And you can't just soak a puddle of burning gasoline, I guess.
No, absolutely not. Because if you spray water on flowing burning fuel, the fuel simply floats on top of the water and it keeps burning. Sometimes it even spreads the fire further because the water acts like a river for the fuel.
Oh, wow. That makes sense.
Yeah, so you have to address the vapor layer that's sitting just above the liquid.
Which is a totally different physics problem.
Okay.
And then we have Class C, which introduces a terrifying new element-energized electrical equipment. Electrical panels, motors, live wiring.
I assume the defining characteristic here is that the fuel source is actively generating its own heat through the electrical current.
That's part of it, yeah. But crucially, the environment is a massive shock hazard.
Right.
The extinguishing agent you use simply cannot conduct electricity. Otherwise, the current travels right up the stream and literally electrocutes the person holding the nozzle.
That is horrifying. And then the document gets into the genuinely exotic, like ultra-high temperature fires, Class D. This involves combustible metals and alloys, magnesium, aluminum, titanium, lithium. These are incredibly dangerous because they burn at blindingly high temperatures, sometimes over 5,000 degrees Fahrenheit.
5,000 degrees.
Yeah. Standard extinguishing agents don't just fail here, they can actually react chemically with the burning metal and cause violent explosions, so they require their own dedicated arsenal.
Wow. And finally, rounding out the 5, we have Class K, which stands for kitchen fires, combustible cooking oils, animal fats, and vegetable oils, which takes us right back to that 600-degree vat we mentioned in the intro.
Exactly. Okay, let's unpack this. We have our 5 enemies, A, B, C, D, and K. Now, how do we actually kill them?
Yeah, the training document outlines 4 primary extinguishing methods: cooling, smothering, chain breaking, and saponification.
Right. And these 4 methods represent the exact mechanisms we use to dismantle that chemical equation we talked about. Cooling is probably the most intuitive one.
Just lowering the temperature.
Exactly. You are applying an agent that absorbs heat faster than the fire can generate it, which drops the fuel below its ignition temperature. Smothering, on the other hand, shifts the attack from temperature to oxygen.
It's essentially starvation.
Yes. You are physically excluding oxygen from the burning process, so the fire literally chokes to death.
I mean, I can easily visualize cooling and smothering, but then we have chain breaking, which sounds like something straight out of a science fiction movie. How do you, break a chain of fire?
Well, fire isn't just heat and fuel, It requires a continuous, self-sustaining chemical chain reaction at a molecular level just to keep generating those flames.
Okay.
So certain chemical agents don't focus on cooling the area or choking off the oxygen. Instead, they physically bond with the free radicals in the flame, interrupting that chemical reaction directly. The burning process is just halted mid-step.
That is wild. And the fourth kill method is saponification. I was reading the notes on this, and the chemistry is just crazy. So smothering is like throwing a heavy blanket over a campfire, but saponification is like hitting a deep fryer with a chemical that literally transforms the burning fat into a suffocating, soapy crust.
That is a highly accurate way to picture it, actually.
Hey, really?
A soap crust.
Yeah. The alkaline chemical agent reacts with the fatty acids in the burning cooking oil, and it triggers a literal soap-making process right on the surface of the boiling oil.
Wow.
This thick, soapy crust seals off the oxygen and traps the combustible vapors underneath. And understanding these highly specific kill methods is just vital.
Because if you get it wrong...
Right. If you try to use a cooling method like spraying plain water on that Class K grease fire, the water sinks below the 600-degree oil, instantly boils into steam, expands massively in volume, and ejects all that burning fuel right into the air. Which brings us to the arsenal itself. Knowing how these fires die leads directly into the chemical weapons engineered to execute those specific methods. And looking at the specs for these handheld extinguishers, the operational limits completely threw me off.
How so?
Well, I kind of assumed all extinguishers emptied in 30 seconds. But the standard water extinguisher, which is for Class A fires only, holds up to 2.5 gallons and is rated to operate for an astonishing 30 to 60 minutes. How is that even physically possible?
Think about the nature of a Class A fire. Like we said, wood and paper smolder deep down within their core.
Right.
If you just blasted all your water in 30 seconds, you might knock down the surface flames, but the deep-seated embers would just reignite minutes later. A 30 to 60-minute operational time allows you to thoroughly soak and penetrate the fuel.
I see.
It shoots a stream 30 to 40 feet, giving you incredible endurance to cool the environment over a long period.
Okay, that endurance makes sense for solid materials. But moving to Class A and B fires, we have AFFF, which stands for Aqueous Film Forming Foam. This one comes in a 2.5-gallon size, shoots 20 to 25 feet, and lasts roughly 50 minutes.
Yeah, and AFFF works by spreading a very thin aqueous film over the surface of a burning liquid fuel. It literally separates the fuel from the oxygen in the air. It is incredibly effective on hydrocarbon spills.
And then we hit the multi-purpose heavy hitters, the dry chemical extinguishers. Specifically, the document highlights monoammonium phosphate for Class A, B, and C fires. They range from 2.5 to 30 pounds, shoot 5 to 20 feet, and operate for 8 to 25 minutes.
And those dry chemicals are the chain breakers we discussed earlier. They interrupt the chemical reaction. The document also notes other variations depending on the exact hazard environment, like sodium bicarbonate, potassium bicarbonate, or potassium chloride.
Right.
They coat the fuel in a fine powder, stopping the reaction instantly.
We also have dry powder, specifically sodium chloride plus, which is engineered exclusively for those ultra-hot Class D combustible metal fires, up to 30 pounds, but it only shoots 4 to 6 feet and operates for 28 to 30 minutes.
You really have to get in close with that one.
Yeah, clearly. And for the kitchen, the wet chemical extinguisher. Potassium acetate for Class K only. 2.5-gallon size, 8 to 12-foot stream, operating for a massive 75 to 85 minutes. I assume the incredibly long duration is to ensure that saponified crust stays cool and doesn't break down while the oil is still boiling hot beneath it.
Spot on. You have to maintain that soapy seal until the entire vat of oil drops completely below its self-ignition temperature. And that takes a very, very long time in a commercial fryer.
Now, we also need to talk about the clean agents. These are the modern replacements for the old Halon 1211 and 1301 systems that were just devastating to the ozone layer. They cover Class A, B, and C fires using chemicals like Fe36, which is hexafluoropropane, or various HFCs, HTCFs, and PFCs. How do these actually differ from the dry chemicals?
Well, dry chemicals leave a fine dust literally everywhere. If you spray a dry chemical extinguisher in a server room, the fire's out, sure, but the corrosive powder will permanently ruin hundreds of thousands of dollars of sensitive electronics.
Oh, that's a nightmare.
Right. But clean agents interrupt the chemical chain reaction, and then they discharge as a rapidly expanding gas. They leave absolute zero residue, the fire dies, and the equipment remains pristine.
That's amazing. But I really want to challenge the specs on the CO2 extinguisher. Carbon dioxide, rated for Class B and C fires, smothers the fire by displacing oxygen, leaves no residue, holds up to 20 pounds, but the stream distance says 3 to 8 feet. You're telling me I have to step within a few paces of a live electrical panel fire or a burning pool of gasoline just to use this? That sounds like a major design flaw.
What's fascinating here is the absolute trade-off of physics. CO2 is brilliant because it displaces oxygen and dissipates completely. But because it is a gas being expelled under pressure, it has terrible aerodynamic reach compared to a heavy, cohesive stream of water or foam.
Just because it's so light.
Exactly. The gas simply cannot punch through the ambient air resistance over a long distance. It billows and disperses way too quickly. So yes, the tactical trade-off for a clean, residue-free kill is that you have to get uncomfortably close to the threat.
It really highlights how these are highly specific, deeply flawed tools if you try to use them outside their exact parameters.
Absolutely.
But everything we've talked about so far, these handheld extinguishers, they are strictly for incipient, early-stage fires. To see how these chemical principles scale up, we need to examine the heavy artillery. The training document goes into this intense, mathematically precise detail on how professionals deploy a foam line from a fire engine.
Oh, this is where it goes from a reactive tool to a highly coordinated tactical operation. The pre-task verbiage alone demonstrates the strict safety protocols. Before a student is even allowed to touch the hose line, they have to run through a rigid verbal checklist.
I was reading that list. They have to physically say out loud, I am in full PPE, personal protective equipment. I will notify the IC incident commander. I will notify the exterior and interior crew. I will work uphill and upwind.
Uphill so flowing, burning fuel doesn't run down toward their boots, and upwind so the wind carries the immense heat, smoke, and extinguishing agent toward the fire rather than blowing it right back into their faces.
Makes total sense. They also have to announce, I will shut down utilities and I will find a second means of egress. Always have an escape route. But there's this one detail that I found mesmerizing. Throughout this setup, every single time they handle a female coupling for the hoses, they have to visually inspect it and verbalize, gasket, swivel, what exactly are they looking for there?
It's basically building muscle memory for disaster prevention. The coupling is the metal fitting that connects the hoses. Inside the female end is a rubber gasket that creates a watertight seal.
Okay.
If that gasket is missing or damaged, the hose will leak massively and lose the water pressure you desperately need to fight the fire. And the swivel is the rotating collar that allows you to thread the hoses together without twisting the entire 50-foot length of heavy hose.
Oh, right, because you couldn't spin the whole hose.
Exactly. If it doesn't spin, you can't connect the lines. In the blinding chaos of a fire, you cannot assume your gear is perfect. You check the seal, you check the spin, and you say it out loud.
So the area is secured. They check your debris, and the black gasket on the reducer, which I assume is the adapter stepping down the hose size.
Yeah.
And then they have to do the math to match the foam to the fire, because you don't just load one universal foam into the fire engine.
Not at all. The math starts the second they identify the fuel. If it's a Class A fire, ordinary combustibles, they select class of foam and set their inline adductor to a 1% mixture.
And just to clarify for everyone, the inline adductor is the device sitting between the hose lines that actually pulls the chemical foam concentrate out of its bucket and mixes it into the water stream, right?
Yes, exactly. The water flowing through the adductor creates a vacuum that sucks the foam up. Now, if they encounter a hydrocarbon fuel, fire like gasoline or diesel, they need AFFF or FFFP foam, and they set the mix at 1, 3, or 6%, depending on the specific product. But the high stakes come with polar solvent fires.
Polar solvents being things like ethanol, methanol, or acetic acid.
Right. Polar solvents mix with water. If you spray standard foam on an ethanol fire, the chemical properties of the solvent will physically attack and dissolve the foam blanket. The protection just disappears.
Wow, so the foam just vanishes.
Pretty much. So the firefighter has to switch to a specialized ARAFFF foam alcohol resistant foam, and they must set the eductor precisely at 6%.
It's literally chemistry on the battlefield. But the physical setup has these incredibly rigid limits. The hose connected from the eductor to the nozzle has to be at least 50 feet long, but absolutely no more than 200 feet. And then there's the gravity rule. The inline eductor cannot be more than 6 feet above the liquid surface of the foam concentrate.
Wait, hold on. You have a massive diesel-powered fire engine pumping water at incredible pressure, and the entire chemical operation is defeated by just 6 vertical feet of gravity. How does that even make sense?
It all comes down to friction loss and atmospheric pressure. The water rushing through the eductor creates a vacuum, but that vacuum is very fragile. As water travels through a hose, it rubs against the inner lining. That friction eats up the water pressure.
So if you exceed 200 feet of hose, there is so much friction loss that the pressure drops, the vacuum fails, and no foam gets sucked up. And regarding that 6-foot rule, the vacuum created inside the eductor only generates enough lift to pull that thick, syrupy chemical concentrate a maximum of 6 vertical feet against the force of gravity. Place the bucket 7 feet down, and the vacuum just pulls air. You end up blasting plain water at a fuel fire.
That is super precarious. So the math is dialed in, the lines are perfect, and it's time for execution. The operator charges the line by calling out, "Water, water, water!" To warn the crew, the hose is about to become a high-pressure battering ram. They declare, "I am agitating the foam." But here is the critical part. They have to open the nozzle's bail, the lever that controls the flow pulley, but they have to do it pointing away from the fire first. They establish the right solution before they face the flames. Why turn your back on the emergency?
Think about the physics of that hose line. When you first open the nozzle, the water currently sitting in the hose hasn't mixed with the chemical foam yet.
Oh, it's just plain water.
Exactly. If you point it directly at a gasoline spill immediately, you are blasting a 50-foot column of raw, unmixed water right into a chemical fire. Best case, it does nothing. Worst case, it spreads the burning fuel across the street. You point away, wait a few seconds for the thick, white finish foam to reach the nozzle, and only then do you engage the threat.
And when they finally face the fire, the way they apply the foam is totally fascinating. The training outlines 3 specific methods: bank down, roll, and rain. Here's where it gets really interesting. They are basically playing tactical billiards with fire-retardant foam.
That analogy is perfect, actually. You never shoot a high-pressure stream of foam directly into a pool of burning liquid. The sheer kinetic energy of the stream will churn the fuel, break the surface tension, and agitate the fire. It completely defeats the entire purpose of smothering it.
So with the bank down method, they aim the stream at a wall or an object just behind the fire. The foam hits the wall, bleeds off its kinetic energy, and gently flows down onto the burning surface to create a delicate seal.
Right. And if there is no wall, they use the roll method. They aim the stream at the dirt or the pavement just in front of the fire, piling the foam up and letting the forward momentum gently push it so it rolls over the top of the burning fuel without piercing the liquid surface. Or, if the environment allows, they use the rain method.
Which is just shooting it straight up.
Basically, they point the nozzle up into the air and let the foam fall gently down on top of the fire like snowfall.
It is incredibly elegant for such a chaotic environment, but obviously most of you listening are not going to be deploying a 200-foot professional foam line. Which brings us back to the civilian battlefield. What happens when you are alone in a hallway with just that red canister on the wall? The source material makes it super clear. Flawless civilian execution requires the exact same tactical discipline as the professionals.
The pre-fight check is so critical for a civilian. First, immediate threat assessment. The document specifically notes that Class D metal fires and Class K kitchen fires are classified as IDLH, immediately dangerous to life or health. You have to respect that heat. If you are not trained, you evacuate.
Then, if you are going to fight, you locate your path of egress. Never let the fire get between you and the exit. If you're outdoors, approach from the windward side so the wind is at your back. And crucially, just like the professionals testing their foam line away from the fire, you must test your extinguisher before you approach the flames.
You have to point the nozzle in a safe direction and discharge the agent with a quick, short burst. Fire extinguishers just sit there unmaintained for years. You do not want to confidently walk up to a raging fire, squeeze the handle, and discover the pressure gauge was broken and the tank is entirely dead. Test it first from a position of safety.
And during that test phase is when you pull the safety pin. Which brings us to the golden acronym of fire extinguishers, PASS. Pull the pin. Aim the nozzle at the base of the fire, squeeze the handle, and sweep the agent across the entire width of the base.
But the document highlights some crucial nuances and severe warnings that go way beyond just remembering PASS. For instance, when dealing with Class B liquid fires or Class K cooking oils, it explicitly states you must never plunge the agent into the fire.
Let's paint that picture again. The 600-degree vat of oil. Someone panics, ignores the sweeping motion, and plunges the stream directly down into the center.
The physical force of a pressurized chemical stream acting on a deep vat of liquid acts like a bomb. It punches a hole right through the surface and violently displaces the boiling, burning fuel underneath. It forces the oil up and out in a 360-degree radius.
Oh, God.
Yeah. You haven't smothered the fire. You have thrown burning oil onto the walls, the ceiling, and yourself. That's why you must use the gentle rain method or deflect it off a nearby surface.
And the document gives a similar severe warning for Class C electrical fires. Even though the extinguishing agents used like CO2 or dry chemicals are non-conductive, extreme caution is still required. It says whenever possible, you must disconnect or turn off the power supply first.
Because once the main breaker is thrown, that energized Class C fire immediately reverts to just a Class A or Class B fire. It stops generating its own electrical heat. It's just burning plastic and wire insulation at that point, which is vastly easier and safer to extinguish.
And finally, the aftermath. The fire goes out. What do? The procedure states you must back away from the fire area. Never turn your back on an extinguished fire because oxygen can rush back in, vapors can accumulate, and it can flash back in an instant. Keep your eyes on it as you retreat. Then you tag the extinguisher for recharge or lay the empty cylinder on its side so nobody else grabs a dead tool in a panic.
That is a vital last step.
So what does this all mean? We started this deep dive looking at a boring red canister on the wall. But by walking through this training document, we've gone from the biological vulnerabilities of solid versus liquid fuels to the chemical chain-breaking properties of modern agents, to the incredibly specific fluid dynamics of a 200-foot professional foam line.
It shifts our understanding entirely, I think. Putting out a fire is not about brute force. It is entirely about applied chemistry, physics, and tactical discipline.
But this raises an important question, something for you to mull over moving forward. The source material meticulously categorizes fires from Class A to Class K based on traditional fuels we've used for decades: wood, gasoline, electrical panels. But as our modern world rapidly changes, it's filling up with entirely new materials. Massive residential lithium-ion battery walls in our garages, entire skyscrapers wrapped in novel synthetic green energy composites. How long is it going to be until the firefighting community is forced to invent a Class X fire? And what wild, undiscovered chemical agents is science going to have to engineer to save us from the fires of the future?
The enemy is constantly evolving, which means the chemistry has to evolve right alongside it.
Absolutely. The next time you walk down the hallway and you pass that invisible red canister on the wall, I hope you don't just see a metal tube. I hope you see the precise math, the engineered chemistry, and the tactical discipline resting silently inside it, just waiting for the exact moment it's needed. Keep questioning the hidden complexities of the everyday objects around you. Thanks for taking this deep dive with us.